Alrighty, good morning or good afternoon, ladies and gentlemen. Happy Wednesday or whenever this catches you. Today I'm going to start on something I like to call patterns in our workbook. This is technically the start of Chapter 4. And Chapter 4 has a special name that'll be important to us later. It is called linear relations. So where I'm actually going to start, before I even go into what a linear relation is, we're going to talk about patterns. And we're going to see if we can come up with some rules and some ways to help us kind of figure these out on a larger scale. So we're going to start simple. We're going to look at the following sets of numbers and try to find the next 3 digits. By the way, I'm putting these notes up on to Teams in our class notebook, so you'll be able to access them. I'm also going to upload this as a digital Word document so that you can print this off and then you can just add notes into it, or if you're watching the video, you can follow along. So I'll put that in the announcement, but you'll be able to download and print this because this is technically different from what's in our workbook. So let's jump right in with our first example. So I have a set of numbers here, and it starts with 1, 8, 15, 22, 29, and then the dots mean that it keeps going. So the purpose of this is that we want to find the next 3 digits in this. Now this one's probably not too hard to see, but how I go about solving this is I want to think about how much it changes in this first jump. So I notice 1 and 8. So to go from 1 to 8, I have to add 7. Okay, well that's our first thing. Let's see if it keeps this pattern. So 8 to 15, I have to add 7. Okay, I'm starting to feel pretty good about this pattern. 15 to 22, yep, I have to add 7. And then finally, 22 to 29, I'm adding 7. So I can see here, each time I go to the next step, I'm going to add 7. So if I want to find the next value, I'm going to think to add 7. So then my next number would be 36. I'm going to add 7 again for the next one. So this is my first. My second one, I'm going to jump up by 7 again. So I'm going to do 36 plus 7, and that gives me 43. And then last one, because they wanted 3 extra digits, I'm going to add 7 one last time. Sorry, I wrote a 3 there. And that's going to give me 50. Cool. So let's try a different one. This one, I don't start at 1, I start at 6. That's okay. I need to think about going from 6 to 11, then to 16, then to 21, then to 26. The first thing I like to think about is how much does the first one change by? So 6 to 11, I am adding 5. And then 11 to 16, I'm adding 5 again. And one of the ways that you can get these numbers, if you're having a hard time, you can always try 16 minus 11. So you're taking this number minus the previous one, and that's going to give you 5. So you can use that as a method. Then I notice, and one of the ways I can actually make this one a little bit faster is I notice it goes 6, 11, 6, or like 6, 1, 6, 1, 6. So the last digit is always a 6 or a 1. This type of pattern is usually going up by 5s. If it goes 2, then 7, 2, then 7, it's going up by 5s. 0, 5, 0, 5, same idea. This is a pattern of adding 5. So I can see I'm adding 5 to each of these. I'm going to add 5. I'm going to get 31. Add 5 again. I'm going to get 36. And add 5 a third time, and I'm going to get 41. So far, this is just simple patterns. We're taking them to the third digit past what they've given us. This one, it gives us one fewer, but it goes 43, 32, 21, 10. Oh, it's going down this time. Well, I can actually still do the same thing. I can do 43 minus 32, and that's going to give me 11, but I'm going down, so it's going to be minus 11. So I'm going down by 11, 32 to 21, down by 11, 21 to 10, the difference is again 11. So I'm pretty confident that this pattern is going down by 11. Where this might come in or where this might give us a bit of troubles. Next one, we're going down by 11. So 10 minus 11 gives me minus 1. So negative numbers are totally okay in this. I'm going to go down by another 11. So this is going to give me negative 12. And then negative 11 is going to give me minus 23. So one of the tricks here, or one of the things that might be causing troubles, is that the last digit goes 3, 2, 1, 0, and then it goes 1, 2, 3, and it's going to go 4, 5, 6, 7 if we keep going. Just be careful when your pattern switches from negative to positive that you're adding the right amount. I definitely see that come up once or twice. All right, next pattern, super tricky one, 7, 7, 7, 7, 7. Well, we can probably guess what the next three are going to be without even thinking about it. It's going to be 7, 7, and 7. But what's actually happening here is the pattern is that I'm adding 0. I'm not changing it. So 7 plus 0, oh, that's 7. And I can keep going. Okay, so the next pattern, we can see it's a pattern. So it goes 2, 3, 2, 3, 2, 3. But this one is a little bit different from before. So notice how the first step I'm adding 1, and then the second step I'm subtracting 1. And then the third step I'm adding 1, and then I'm subtracting 1, and so on. It's still a pattern. I can still guess that the next digit's going to be 2. I can follow the pattern of taking away 1 and then adding 1 to get back to 3, and then taking away 1 to get to 2. So there's no issue with it being a pattern, but you can maybe see a difference between these ones. If not, that's okay. We're going to visit another pattern, and we can see that it's a pattern, or you'll be able to see in a moment. But again, this one has a little bit of a difference. So this one is now 2, 4, 8, 16, 32. Well, this one I'm adding 2, and then this one I'm adding 4, then I'm adding 8, then I'm adding 16, and then if I follow this pattern, I'm adding the number that's previous. So to get to from 2 to 4, I'm adding 2, and then from 4 to 8, I'm adding 4, and then 8 to 16, I'm adding 8. So I'm adding the number previous to it. So this jump, I'm going to think to myself, I'm going to make it a little bit bigger so it's easy to see. If I'm following the pattern, I'm going to add 32, and I'm going to get to 64. Then I'm going to add 64. It's going to get me to 128. And then finally, I'm going to add 128 to get me to 256. Now, what I want to point out that's happening here, I can think of it as addition, but one of the things you can maybe see is if I go from 2 to 4, one way that I can do that is I can multiply it by 2. And then I can go from 4 to 8, and I can multiply 4 by 2, and I get to 8. And then 8 times 2 gets me to 16, times 2 gets me to 32, times 2 gets me to 64. So all of these are powers of 2. For example, 2 is 2 to the power 1, then I have 2 to the power 2, 2 to the power 3. So you can connect this to our powers unit. Like I said, it's still a pattern, but now the pattern has changed slightly. And so I'm going to back up, and I'm going to say a bold statement that these first 4 examples that I gave all have something in common that is different from these ones. Can you see it? It's a little bit hard to see because we're looking at the pattern. Take a look at how much they change by. So the first 4 examples, we can always think of it as the new digit changes by the same amount. Every time. So it doesn't matter if I'm the 4th number in the pattern or the 10th or the millionth, I'm doing the same thing. In the first example here, I'm always adding 7. if I'm in the second example, I'm always adding 5 to the previous answer. I'm always adding 11 in the third, or subtracting 11, sorry, and then the last one I'm leaving alone and adding 0. Whereas with these ones, the change in values is different for the next number. So in this example, I go up by 1 and then I go down by 1. So it's changing by a different amount. The change is 1, but in one case I'm going up and then I'm going down and I'm going up and then I'm going down. So it changes by a different amount each time. It's not going up by 1 and then up by 1 and then up by 1. And then likewise, the 2, 4, 8, 16, 32, 64, 122, 56, my gaps are getting bigger and bigger and bigger. I'm adding 2, and then I'm adding 4, and then I'm adding 8. I'm adding a different value each time. So why this is important, we'll actually get into in a little bit. But one of the things I'll hint is examples 1 to 4 are what we call linear relationships. So we'll talk about why that's important and why we can use that to help us. But for now, when we think of a linear relationship, I want us to think about the pattern changing by the same amount. It can be adding, it can be subtracting, it can be adding a decimal value. That's not an issue so long as it adds or changes by the same amount for each step that we take. Let's look at this now with some pictures. So, example 1 here, this is a pattern. I can see that there is some way that I can combine this and move it forward. So I'm just going to take a screenshot to make this easier. So again, I want to come up with the next 3 in the series. So I'm going to go 1. Whoops. Sorry about this. 2, and then 3. So I'm going to spread them out a bit. So I can think about what the next one's going to be. But before that, let's take a look at just these 4. So I start with the sort of upside down T shape, and I can count how many are in here. There are 4 blocks. But another way I can think about it is each leg of my T leg is 1 box long. So what's changed is I'm going to look for the previous shape and I notice it's right here. So what changed was I added 1 box to each end. Okay, well then now I'm going to look for this shape in my next example. So I'm looking for a T or an upside down T that's 2 long on either side. So 1, 2, 1, 2, 1, 2, and then the joining piece. So again, the new boxes are right here. So again, I'm adding 1 box to each end. Another way I can think about this is each jump, if I'm adding 1 box to each end, is I'm going to go up by 3, I'm going to go up by 3. So again, I'm looking for the previous shape, so now I'm looking for 3 long on each side. So our original or our last shape is right here, and then our new ones are right here. So I'm feeling pretty confident at this point that my pattern, if I'm going to add in boxes, I can do 1 box here, one box here, and then one box here. And since you know what, I'll get rid of these two. What I'm going to do is take this, copy, paste. So this is my next one in the pattern, and I'm going to add one here, one here, one here. And then if I wanted to do one more, I'm going to follow that same pattern and go one box, one box, one box. Okay, not too bad. This one, think about whether or not it's linear or not. So think about how much we're changing by each time. Before I give you the answer, I'm going to look at this example here. So I start with one triangle as my shape. The next one, I'm going to be counting this with small triangles. So my original triangle, I'll say, is this one here. And then I have added 1, 2, 3 new triangles. So 3 new triangles, I'll just draw a triangle. And it forms a larger triangle. That's sort of our pattern, at least so far. So now I'm going to look for this design for the next one. And I can see, or at least I can make, if I draw this in red, you can see that I can make that previous one right here. So I'm picking the bottom left corner. Now I'm going to see how many new triangles I add. Well, I have 1, 2, 3, 4. And I'm just counting small triangles. I'm not counting legs. It's just how many triangles, either right side or upside down, I can make. But now I'm adding 5. So plus 5 triangles, and again, it makes a larger triangle. So I go up by 3, then I go up by 5. I can guess that I'm going to go up by 7, because that's the pattern that I see here. But let's do it a slightly different way. Let's actually just draw what we can imagine the next pattern is. And to do that, again, I'm going to use my screen capture. I'm going to make this triangle over here. There we go. And from here, I'm going to look for this shape here. So I'm looking for 1, 2, 3, 4, 5. Well, sorry, I've actually made this shape, but I need to make it bigger. And what I notice is that it gets 1 taller each time. So I need to go 1, then I go 2, 3, 4, 5, 6, 7. So I see that if I want to make a bigger triangle, and I'm going to make this a little bit neater for us, I can draw better than what I have been. So if I follow this pattern, I get this sort of triangle, so I can count up how many new triangles I've made. So I've made 1, 2, 3, 4, 5, 6, 7. So this actually agrees with this very nicely. If I wanted to go one step further, I would make this triangle even bigger. So I would continue with this big triangle here, and we can guess that I'm going to add 9 on. And if I really quickly just kind of go like 1, 2, 3, 4, 5, 6, 7, 8, 9. I can see that to make it 1 taller, I need to add 9. And then the next one I would have to probably add 11. I'm not going to draw that just for time's sake, but if I look at these two, this one our first example with the boxes is going up by 3 each time. I'm adding 1 to each end. So what I can say is this one is an example of a linear relationship because I'm changing by the same amount. This one, I'm just going to say for right now it's non-linear because it changes by a different amount. And I'll make a note of that. So key takeaway from this, linear relationships change by the same amount for each step in a pattern. Non-linear relationships change by a different amount for each step in their pattern. All right, so next up, what I want to cover is this is good for a couple of patterns that we've been doing. Like for each of these, we've gone 3 digits further. But what if I want to say I don't want to find the next digit or the next third, but instead I want to find the 100th digit. I want to find something better than just going forward a little bit at a time. So I'm going to take our first example where I was going up by 7 each time. So as a reminder, we're going up by 7 here, and see if I can make an equation for this. So my goal is to make an equation. Now, the way we can think about this is I add 7 a bunch of times. And one of the things that we've talked about before, one of the things that you'll have learned previously is that repeated addition is the same thing as multiplication. Example, if I have 7 plus 7 plus 7, this gives me 21, I can rewrite this as 3 times 7 to give me the same value. So what I notice here is that I'm going up by some amount. So for each step, so I'll write it out, for each step up in the pattern, I go up by 7. So a good place to start would be my total equals 7 times x, or 7x. So if x is equal to 1, my total, which I'll recall t would be equal to 7 times 1, which would give me 7. If x was equal to 10, I would get t is equal to 7 times 10, so this would give me 70. Now the issue is 7 actually isn't in my pattern. So I need to think about where I'm going to start. I actually start at 1. So a good place to start would be, I notice that each one of these is 1 above. So I'm going to start with t is equal to 7x plus 1. Well, now if I have x is equal to 1, t would be equal to 7 times 1 plus 1, which is going to give me 8. If I do x is equal to 2, I'm going to get t is equal to 7 times 2 plus 1, which is going to give me 15. So I have the second and I have the third one. So what I can say for this starting value, this 1, I can start with x is equal to 0, because if x is equal to 0, then I can go t is equal to 7 times 0 plus 1. So 7 times 0 gives me 0 plus 1, so I get t is equal to 1. That goes away. So the equation I can use in this case would be t is equal to 7x plus 1, or I might say, I can rewrite it a different way, but I'll leave it like that. Basically, each one goes up by 7. That's how I get this piece here, and then I start at a value of 1. So I start, and then I'll think of this as a step. Each step I go up by 7. So each time x goes up by 1, I'm going to jump up t by 7, and I start at 1. Okay, let's look at a slightly different example. They want to calculate the perimeter of the 10th set of blocks. So again, we have a pattern here. I could technically go 1, 2, 3, 4, and keep going this pattern so that there's 10. But I don't want to do that. So I'm going to look at how we calculate perimeter. I'm going to assume each of these sides is 1. And when we calculate perimeter, so I'll call this shape 1. So P, the perimeter of the first shape is 1 plus 1 plus 1 plus 1. Each of the sides is equal to 1, so this gives me a perimeter of 4. Then I look at here, I'm only counting the outside, so this one and this one are still 1. But now this side and this side are 2. So the perimeter of shape 2, which I'll call here, is equal to 1 plus 2 plus 1 plus 2 equals 6. I don't necessarily see a pattern yet. Here, I've got 1 for my shape 3, and these ones are now 3 long. So the shape of P3 is equal to 1 plus 3 plus 1 plus 3 equals 8. Now, one of the things I notice, 2 of the lengths are changing each time by 1, and the final answer, which is the one that I'm more concerned with, changes by 2. So I can rewrite the perimeter here, perimeter of the nth block. So I'm going to use n to represent the nth set in this case, or in this pattern. So I'm starting with, for this one, I'm going to have n is equal to 1, n is equal to 2, and n is equal to 3. Totally fine to do that. So I notice I start at 4, and I jump up by 2. So my step is equal to 2, and I start at the perimeter equals to 4. Because I'm starting at n equals 1, I'm already 1 step in. So what I have to think about is what I'm going to start with to give me 4. I have 1 step of 2, and the way we can think about our other value is what stays the same. So I notice that I'm adding blocks onto the side, but in every example, these sides are 1. So there's 2 of them, and because I'm adding with perimeter, my 2 sides are staying the same, so I have a length of 2 that does not change. So an amount that doesn't change is going to be what I add on to the end, and my step is equal to 2, so I can rewrite this as 2 times n plus 2. And we can see that if I go n is equal to 1, I'm going to get 2 times 1 plus 2 gives me 4. N is equal to 2, so I have 2 times 2 plus 2. It's going to give me 6. This is 4 plus 2. And then finally, n is equal to 3. 2 times 3 plus 2. So this part's going to give me 6. And then add a 2 onto it is going to give me 8. So I notice that my pattern works for all 3 of these. So now I can try n is equal to 10. I don't need to draw it. So now I have the perimeter of the 10th block is equal to 2. I'll plug in the 10 plus 2. So 2 times 10 gives me 20 plus 2. So the 10th one gives me 22. And that should be our answer. So one of the things, look for a step and look for a starting point. So in this case, we're starting with these sides that don't change, and then each time the other two sides get bigger by 1 each, so I go up by a total of 2. All right. Well, second to last example, we want to write an equation relating x to n. So this is going to be actually a big bulk of our course. So I want to look at how n changes and how x changes. So I start at n equals to 0, I go up by 1, I go up by 1 to 2, I go up by 1 to 3, I go up by 1 to 4, and finally I go up by 1 to 5. So n changes by 1, and then I'm looking for a consistent value between our x values. So 2 to 8 gives me a value of 6, 8 to 14, oh, it's still 6, 14 to 20, still 6, still 6, still 6. So how we can think about this is for every 1 that n goes up by, x increases by 6. So for every time that n gets bigger by a value of 1, I'm going to increase my value of x by 6. So my step, in this case, is going to be 6. My starting point, it actually gives me an n is equal to 0. So where we start, we're going to start at n is equal to 0. What does x equal? Or the way we can think about it is, before any steps are taken, does x have a value? Otherwise, if I went up just by steps of 6, I would go 6, 12, 18. It would just be multiples of 6. So x seems to have a little bit extra added each time. I notice that this is 2 away from 0. I know that this is 2 away from 6, 2 above 12. So the multiples are all there, but they're increased by 2 for each of them. So the way I can treat this is x is equal to 6 times n. So again, this is my step, plus my starting value. So in this case, my starting value was 2. And the way we can think about it is when n equals 0 is another way. So when it asks to write an equation, it is looking for this. And what you can do, just to double check, is plug in n is equal to 0, n is equal to 2. You can try out a few of them. For each one, I should get x is equal to 6 times 0 plus 2. So I get x is equal to 2. Good. I want to make sure it works for more than just 1. So I'm going to try 6 times 2 plus 2. So I get 12 plus 2, so x is equal to 14, also good. So if it works for 2, or even if I want to go one more and try it for 3, that'd be me being really safe, so I'll try n is equal to 5. So I would get x is equal to 6 times 5 plus 2. So I got 30 plus 2, so x is equal to 32. Okay, I know for certain that I'm good because I have these pairs here, and they match up perfectly. So notice how I have n is equal to 0, x is equal to 2, n is equal to 2, x is equal to 14. I'm basically just taking these and turning them into an equation. All right, the last example I'm going to show today is a word problem. It's from 4.1. This is definitely a spicy word problem, but you'll be able to see how I can solve this in a very similar way to the above problems. So I'll read the question out first. And there's actually going to be a discussion question for marks that we're going to put into teams. So the question reads, in 1994, 45% of the students graduated from university in less than 5 years. In 2000, 41% of students graduated university in less than 5 years. So question A asks, write an equation relating the year of graduation to the number of years spent in university. So this part here, we're looking for a percent. But I'm going to start with my guess method. So I'm going to start with my givens. So it tells me 2 years of graduation. So I'm going to actually make a column table, and I'm going to make a third column, and you'll see why in a second. So I'll have year of graduation. So I have 1994, and I'm going to make a gap because there is a 6-year gap between these two. And then it says 45% of students graduated from university in 1994. So I'm going to do percent of students. So here I have 45%, and then 41% graduated later. So I'm going to put 41. In fact, I'm actually going to get rid of the percentage sign. So we have to make an equation that relates these two things together. So the first thing I'm going to do is give them a variable. So I'm going to call the year of graduation, I'm going to call that G for graduation. And then percentage of students, I'm going to call X. The reason why I'm calling them these is because the year of graduation is going to be the amount that goes up, and the amount of percent students that change is going to be affected by what year it is. So I'm going to look at the change between both of these. Now, here we see our first issue. In our previous tables, this went up by 1. In this case, I go up by 6. And in this case, my percentage of students has gone down by 4. So when I compare these, I go up by a step of 6 and I go down by a step of 4 for my change. Previously, I was going up one at a time for at least one of these. So now we need to think about how they relate to each other. So how does changing G affect X? So how I can do that is I'm going to look at change in X over change in G. And this is going to give me (41) minus 45 over 2000 minus 1994. Or it'll give me minus 4 over 6, which I can reduce to minus 2 over 3. So the way I can think about this is for every 3 years that has passed, percent of graduation goes down by 2%. And we can see if it goes up by 6%, or in 6 years, it goes down by 4%. So if I go 3 to 1997, I'm going to change by 2%, and I'm going to go to 43%. Now, this fraction here gives me the change in every year. So another way I can think about it is every year percent graduated goes down by 0.66%, repeating. Now, one of the good things about these graphs or equations is that I can pick a starting point. Right now, our starting point is 1994. That kind of sucks because it isn't 0. So I'm going to make a new variable. I'm going to call it y, and I'm going to call it years since 1994. I'm going to pick 1994 as my starting point. So now I have 0. If I was to go 3 years ahead to 1997, I have 3, and then I have 6. Now, if I look at this, I'm now starting with much simpler numbers, and I can see I'm starting at 0 and I'm going to 45. I'm going to 3 and I'm going to 43, and then so on. So I'm actually going to use my x and my y to make a relationship. So from here, it looks very similar. I have this, and notice how it hasn't changed. I'm still changing by 3 years. I'm going up by 3 for one, and I'm going down by 2 for the other. So I'm not changing anything by doing this. So then I can write that y is equal to, or sorry, let me change this. X is equal to minus 2/3 y plus, well, when y is 0, my x is going to be 45. So my starting value is this. So step 1, or part A, done. Part B asks, if this linear trend continues, what is the percent of university students that will graduate in less than 5 years? So one option is I can do 1994, and then I can go to 2000. So I go up by 6. I go up by 6 again to 2006, and then I jump up one more time to 2012. So then I can go 45, 41. I'm doing the same jump down, so I'm going to go down by 4, so I'm going to end up at 37, and then finally 33. Boom, I'm done. The issue with this is, what happens if I pick a year that doesn't work well for me? So now, if it wasn't 2012, this wouldn't have worked. So what I'm going to show you is, well, 2012 minus 1994. This will show me how many years after 1994 it is. So I have a value of 18 years. And from here, I can plug in y is equal to 18 into this equation and figure out my answer. So I'm going to have x, the percent of students graduated, is equal to minus 2/3 times 18 plus 45. Whoops. So this is going to give me 18 divided by 3 times negative 2. So divide by 3 first to get 6 times negative 2 to give me minus 12 plus 45. So this is going to give me a value of x is equal to 33%. So again, remember x stands for the percentage of students graduating, so we can answer in a sentence and say approximately 33% will graduate in less than 5 years in 2012. So notice how, rather than relying on this to jump forward a bunch of steps, I can just plug in the number. And why I picked this piece here was because I wanted to use smaller numbers. If I had used 1994 or 1997, notice how I'm now really far in a sequence. I'm still jumping up by the same number of years, but now I would have to figure out my starting point, go all the way back to year 0, and this equation would have a very different value for this. It's still fine, but it would not be as nice to work with. So I'm setting this up to be nice to work with. So that's the last bit I wanted to do. Most of our word problems are going to be more basic than this, but they're going to be in the realm where you're making an equation, so they're definitely one of the more tricky things. So one of the things, I'm going to add a part C to this question, and I'm actually going to make it 4 marks. So I'll put, so in our discussion, channel, replying to the post I make. So that's step one. And what you're going to answer is why might this method of estimating graduation percentages in B be inaccurate? So what I'm asking is, in part B, it asked us to figure out how many people would graduate by the end of 2012. So your response is going to be, why would me using this equation not necessarily be a great way of a university estimating? So think of the numbers, look at the question, and take a look at what details are given to us and what isn't, and try to come up with your own thing. So I'm going to make a post asking this question, and I want to see your response. And I'm going to give participation marks for this, so I want people to chime in and tell me their thoughts. In terms of homework, I'm also going to post, because this is going to be what we're picking up with when we meet again on Tuesday next week. So homework is 4.1. I'll do 3 colors. So our mild questions are 1 to 4, A, C, E, so every second one. Our medium, which I'll put in orange, is 5 and 6, A, C, E. There is a medium spicy this time. So it's kind of spicy, but it's not all the way there yet. I would still give this one a try. Try 7, A, and C. It is the same as 5 and 6, except it deals with shapes. And then last but not least, our spicy questions are 9 and 12. So this is homework, practice for Monday. But for marks, the only thing that's going to be for marks is this question here, and I'm going to put that up on our teams today. So have this answered by Monday. I just want to see what ideas might come out from people talking about this, and then I want to collect our ideas and talk about them, because it'll be good to go over what some of our thoughts about this are. So again, for Monday, for marks, come up with a reason for why estimating this might not be accurate, just for part B. In any case, that's all I have for you today. Take care, stay safe, have a good one.